So, today I want to talk about differential equations. We're going to do a problem set at the very beginning of the class. So, let's talk about what a differential equation is first, before we get into these problems. So, a differential equation is any equation that contains a derivative. You might be used to, in calculus, dy dx equals, let's say, cosine x. Something like this, we have the derivative on the left, the function on the right. The function is of the independent variable. We can very easily solve this for y. We can find a y equals. And you all may have learned this in calculus. We can kind of multiply by the dx. So we have dy equals cosine x dx. And from here, we can just integrate. Integrate both sides, we get y equals integral of cosine sine x plus c. So this is sort of the beginning of differential equations, right? It's an equation that contains a derivative. Now you'll see, like in the problems that we start just now, that things get a lot more complicated. We have a lot of different techniques in order to solve those. So let's begin. Let's just start these problems. So, match the following equations with a direction field. So here we have slope fields or direction fields, and we have these equations. So I'm going to just talk through what I'm thinking through as I'm doing these problems. So we have y prime equals y plus 2. Okay, so I think a great place to start is by setting y equal to 0. And that's actually what this says right here. I'm not going to do this whole process that we're given. I'm just going to think through, what would I do? So the derivative y prime equals 0 plus 2, or 2. So when y is 0, which on the graph, that is the x-axis, along the x-axis, and we're going from -5 to 5 in all of these, and a 0 here. At every point along the x-axis, the slope is 2. So it's something like this, right? Little lines with, maybe that's not 2, but close enough. So it's going to be constant as we move along the x-axis. And actually, we can think about this equation like we have y prime equals y plus 2. If we change x, nothing happens to our derivative. So, a picture where, like, as we move from left to right in the x direction, nothing is changing. This is a good sign. This is likely to be our answer. But let's not go to our answers yet. Let's do the same thing here. Let's set y equal to 0. We have -2x plus 0 over 2 times 0, or -2x over 0. And remember that dividing by 0 means that our slope is undefined. And think about, what does an undefined slope look like? Does it mean there's nothing there? It doesn't mean that there's nothing there. It means that our slope is vertical. So our slope is vertical along the x-axis. Okay. So we should be able to see that one of these pictures. And we can see that 1 and 2 are clearly quite different. And finally, we'll do y prime equals e to the negative x minus 0, or y prime equals e to the negative x. Okay, so this actually is going to change as we move from left to right. If we plug in 0 for x, we get 1. If we plug in 5, it would be e to the negative 5, or 1 over e to the 5th, which is a pretty small number, but positive. If we plug in -5, it'd be e to the negative 5, or e to the 5th, and that's a very large positive number. So we're going to be kind of like lying down, I would say. Like, this slope is going to be sort of slowly lying down, going from nearly vertical to nearly horizontal. Okay, so yeah, we can just kind of take a look here. At our graphs. So starting with C, just because I saw it first, this slope along the x-axis stays at a constant, and that looks like about 2. So that looks like number 1 for us. And looking at B, we are going from vertical, nearly vertical, to lying down. That's what we just described. So that would be 3. And that leaves A, 2 would be A. Now, something that catches my attention here is this is vertical, this is not, and this is vertical but down. I think, so the difference here is really at 0, what's happening. I think this is a mistake by the graphing software, but at 0, we would have 0 over 0, which is indeterminate. And so we'd have to basically take the limit. So maybe this limit approach something like 1/2. Yeah, okay. There's number 1. So we're going to keep going with the same thing here. Let's see. Okay. So 1 set y equal to 0, y prime equals x. So we can, well, we'll do a number line at the end. I'm just going to go ahead and do these. So y is equal to 0 here, we just get 0. Y prime is equal to 0 minus 0, negative x cubed over 6. And y prime equals 2x minus 1. Okay, so now we are depending on x more. But we have this second one with y prime being 0, so that's going to be flat the whole way across. And honestly, if we're doing these problems, I think the smart thing to do would be to just go look for that immediately, because we only have 4 choices. So looking at my choices, A looks good. I mean, the lines are a little off the x-axis, but could just be the way it's drawn. B, this is not 0 the whole time. C is not. D is not. So that makes me think that number 2 is B. Okay, and then let's maybe look at the other 3. What's going on as we move across the x-axis from -5 to 5? 0, 0. Okay, so x at -5 would be -5 down, down more than that. At 0, it's going to be flat. At 5, it's going to be up. So it's going to be kind of transitioning like that, and more up, down, very down. Something like that. That would be 1. 3 would be, if we plug in -5, we'd have -5 cubed, which is -125. Negative 125, though, with this negative sign would be 125 over 6, which is a pretty large positive number. If you plug in 0, we would have 0, also flat. And if we plug in a positive 5, we would get 125. Negative 125 over 6 is a pretty large negative number. And like this, we're going to be kind of lying down. We're going to be kind of transitioning here, something maybe like that. And the last, if we plug in a -5, we get -10 minus 1 is -11, so that's quite negative. If we plug in 0, we get -1. So we're actually not, we don't have a slope of 0 at 0. We have a slope of 0 at, looks like 1/2. And then once again, if we plug in 5, we'd have a slope of 9. So we're going to be increasing. Okay, so it looks like 1 and 4, I'm going to label these 1, 3, and 4. 1 and 4 are quite similar, but the thing to watch out for here is that in 4, the slope is not 0. So let's go ahead and look for 3. Actually, we'll start from a positive slope to going to a negative, and that looks like D, positive to negative, whereas the other are negative to positive, negative to positive. So there's D. What did I say? 3. 3 was positive to negative. So that's D. And then the difference between 1 and 4 is really that slope at 0 is -1. And if I look between these two, C has a slope at -1. So that's C. And that leaves us A. 1 would be A. Oh, sorry. I have done something wrong. What did I do wrong? Oh, I marked these wrong. This one originally that I marked as B, it is number 2, but it's actually A. Okay, sorry about that. Okay. So this looks essentially the same. We're matching up again. So let's do that. By the same method, y prime equals 2, y prime equals, and this is actually a couple of these are the same, so we already know what they look like. Y prime equals 2 sine x plus 1, and y prime equals -2 plus x. Okay, so just a reminder, we were setting y equal to 0 in all of these. And now that we have some experience, like once again, I just want to go through and mark these off as quickly as I can. So number 1, it's a constant slope of 2. So if we look on the x-axis, that's not constant in A, it's not constant in B, it is constant in C. So 1 is C. Number 2, we've already seen as well. That was undefined. So we have vertical slopes along the x-axis, and we don't here. These are changing, but D we do. So there we go. Okay, and so the next one is sine x. Let's see if we can just deal with x. Sine x might be just a little bit more work. And I noticed that these are going from -4 to 4 in this image. So y prime, -2 plus x. At -4, that's going to be a very negative slope. At 0, it's going to be -2, so still quite negative. At 2, it's going to be 0. And at 4, it's going to be 2. So let's just look for something that looks like that. It looks like A would not be correct because at 2 we're quite positive, whereas B, it looks like we're making that transition here at about 2. So, I think this is nice because we didn't really have to deal with sine, but we certainly can. -4, just so you see it. If we plug in 0 for x, we get 2 sine of 0. Sine of 0 is 0, so this would be 1. If we plug in, let's say pi, that's about 3.14 is about here. Pi is also 0, so we'd also get 1 as our slope. Pi over 2 is halfway between, and sine of pi over 2 is 1, times 2 is 2, plus 1 is 3, so it's a little bit more positive. If we go to negative pi, once again, would be sine of 0, 2 plus 1 is 1, and negative pi over 2, sine of negative pi over 2 is -1 times -2. So times 2 is -2 plus 1, and so we'd be like down like that. And we can see that looks somewhat similar. This looks similar to what we've got here in A. Okay. All right, moving on. Okay, so different type of problem. Consider the direction field below for a differential equation. Y prime equals y times y minus 3 times y minus 5. Use the graph and equation to answer the following questions. Find the equilibrium solutions for the differential equation. Okay, so an equilibrium solution, I'm assuming you're not very far into this class, so you probably don't know at this point. An equilibrium solution it's a constant solution where if we start at that solution, we will never leave it. And let's see what that means. Um, so if we look at this graph, if we start here on this dotted line, on this slope field, we're never going to move. Our slope is constantly 0. We're not going to go up. We're not going to go down. We're just going to stay here. Same thing here. And it looks like also at 0. Why these points, though? Well, if we look at our equation, y prime equals y times y minus 3 times y minus 5. If our function just equaled 5, for example, y equals 5, then the derivative of that is 0. And if we plug in here, it would work. We could plug in y equals 5. We would have 5 times 5 minus 3 times 5 minus 5. And that 5 minus 5 will make this whole thing 0. So the derivative y prime would be 0. And it would be when we just take the derivative of the function. So it would work by plugging in and by taking the derivative. The same thing with y equals 3. If we plug in here, 3 times 3 minus 3, and the 3 minus 3 will be what makes it 0. And the same thing with 0. Y equals 0, prime equals 0. Okay. So these would be our equilibrium solutions, 0, 3, and 5. Okay. If the initial condition y of 0 is equal to c, for what values of c is the limit as t goes to infinity finite? Okay, so t is basically our x here, our x-axis, and our y-axis is y. So what this is saying is if our initial condition y of 0 equals c, so y of t, so our y-intercepts are equal to c, for what value of c is this limit finite? Okay, so, we have the whole y-axis we could pick, but what we need to pick are values below, in between, and above our equilibrium solutions. Because let's see what happens. So if we are below it here, we see that our slope is going down very quickly. And it looks like it would just go down forever. And we're actually just thinking about what happens as t goes to infinity, so as we're moving to the right. But you can see what would happen if it went to the left. We would kind of be stuck on this equilibrium. So we would approach this equilibrium solution. And then we have this solution here. We're going up, and then it's not well drawn. Going up, and then we kind of flatten out here as we go along. And we can once again draw what happens as we go backwards. And same here. I'm going to use a different color. Okay. This is what happens as t goes to infinity. Back to red, and we'll see what happens with this value. We basically just go straight up. Okay. So these equilibrium solutions have a great deal of power, weight over what happens to these other solutions. So if we start below 0, before that first equilibrium value, as we go from top to bottom, it looks like as t goes to infinity, we're just going to go straight down. We're going to go to negative infinity. So for what value of c does t go to infinity for y of t? Is it finite? It would not be when C is less than, and I'm going to go ahead and write these intervals. When C is from negative infinity to 0, it would not work. Not work. We're going to negative infinity for those values. From 0 to 3, that's the interval from this solution to this solution, would it work? Well, when we're between 0 and 3, any point along here is going to follow the same pattern that we saw here with this value of C. We will be going up and then stabilizing at about y equals 3. We'll follow y equals 3 to infinity. So yes, this would work for 0 to 3. The next interval would be from 3 to 5. And any value C here would see us going to infinity, but we're going downwards here. We're going down to this solution, and we'll talk about that later, what that means. It's certainly a finite number, though. Certainly a finite value. So that works. And last, from 5 to infinity, does this work? Well, no, it doesn't. We just go up forever. That would approach infinity. Okay, so the interval that would work would be 0 to 3, union 3 to 5. And just to introduce the concept I was referring to earlier, we have something called, for equilibrium solutions, we have 3 types. We have stable, semi-stable, and unstable. Okay. And I want you to look at our solutions y equals 5, y equals 3, and y equals 0. And just think, based upon like what you know the definition of the word stable and unstable to be, I'll give you a hint that there's no semi-stable solutions here. Does y equals 5 look like a stable or unstable solution? Does y equals 3 look stable or unstable? Does y equals 0 look stable or unstable? Just think about it. We don't really need to talk about why these are the case yet. Hopefully you thought that 3 looked stable, 5 looked unstable, and 0 looked unstable. Yeah, and just in words, that's because, if we start below 0, we will always go away from it. If we start above 0, we will always go away from it. If we start below 3, but above 0 in this interval, and as well as above 3 but below 5, we will always go towards 3 as time goes on, as t goes to infinity. And with 5, if we're in the interval from 3 to 5 or from 5 to infinity, we will always go away from it. So it would be unstable. I'll go ahead and mark these 0 and 5. It looks like an interval. Y equals 5, 0, y equals 5, y equals 3. And you might be, wondering what semi-stable is. It means that if we're above it, and I'm going to go ahead and draw that on here. So for 5, like if it looked like this, we're going away from it above it, but we are coming towards it from below, this would be semi-stable. Yeah, we're kind of breaking the rules here. We're breaking the rule of the slope field, but this is what a semi-stable solution would look like. It could also look the same, but going down. And so we're going down towards it, and we're going down away from it. Okay, so those would be semi-stable. Okay, enough there. Consider the slope field below. For the solution that satisfies y equals 0, sketch the solution curve and estimate the following. I don't really love this question, but y equals 0. All we do to estimate this curve is kind of follow this. It's almost like a connected dots, like going up like that. And then we do the same by going backwards. It's kind of weird. Kind of get stuck here. Yeah, and then we're estimating y of 1. It looks like it's about at 0.5, y of negative 1, 0.5, just looking here. Yeah, um, y of 0 equals 1, y of 0 equals 1. Just following this curve again. Okay, yeah, something like that. Estimating y of 0.5 looks to be about 1.5. Y of negative 1 at 0.75, 0.75. And y of 0 equals negative 1. Sorry, got lost there. This almost looks like a constant slope for everything. So y of 1, negative 2, y of negative 1, 0. Okay, yeah, that's really about it there. Okay, consider two slope fields below. I think this question was a little bit, I don't know, there was some issue. Okay, for the slope field in figure 1, a solution passing point through the point 3, 3 has a what kind of slope? So we just go to 3 and down to negative 3. What kind of slope do we have? Like positive. I think we just say positive, actually. I think it's just positive or negative. But it's like about like 1/2. And we can draw this, of course. Looks a bit like a spiral. And I'm not taking my time. I want to get through this part. Negative 2, negative 2. It's very close to the one we've already drawn. Yeah, something like that. A couple of spirals. Negative 2, negative 2. What kind of slope did it have? Negative. Okay, figure 2. Figure 2, 3 comma 2. 3 comma 2. Just looks positive. It doesn't look positive. Yeah, it does. 3 comma 2. Yeah, and it comes negative like that. It's positive. Okay, and 0 comma 3. 0 comma 3 is negative. Very close to the other one. Negative. Yeah, not so interesting. Just drawing the solution curves. Okay. Once again, we're drawing this. 0, 0. Honestly, I think we don't even need to draw these to answer the question. From your sketch, what is the equation of the solution to the differential equation that passes through 1, 0? Okay, 1, 0. So they want us to come up with an equation for this. So we're thinking it must be a graph that looks familiar, right? And it does look quite linear, right? Yeah, let's just give it a slope of 1. So if the slope is 1, mx plus b, we would have m is equal to 1. Our b value is negative 1, so y equals x minus 1. Y equals x minus 1. So, and it wants us to verify our solution is correct by plugging it in. Okay, this is worthwhile. So our derivative would just be y prime equals 1. And so if we plug it into this equation, y prime is 1. X is independent. We're not changing that. But y is x minus 1. So y equals x minus x plus 1. Y 1 equals 1. So great. That does satisfy our differential equation. So it is correct. X minus 1. Okay. Okay, and now kind of continuing from that last problem, for what positive values of k does the function y equals sine of kt satisfy the differential equation y double prime plus 9y equals 0? Okay, at this point in the class, you haven't learned any methods really for solving differential equations. So we could call this like the derivative plug-in method at this point. So the derivative plug-in, derivative plug-in method. Okay, this is when we have a function, y equals, and a differential equation. When you are given a function and differential equation. Okay. So here we have the function y equals sine kt and y double prime plus 9y equals 0 is our differential equation. So our steps here, if we need to outline them as steps, is take all necessary derivatives of the function, plug in derivatives to verify or find constants. Okay, so what I mean by verify is like basically that last problem was we were verifying a solution. We were showing that it did in fact work. In this case, we're going to be finding constants. So let's see this in action. So for number one, we have y double prime plus 9y equals 0. That's our differential equation. We need to take all necessary derivatives of the function. Okay, what I mean by that. We have a y equals, which we could input here for y right now. We could replace y with sine kt. But we do not yet have y prime, so we need to take the derivative d dt of y, sine kt, to find y prime first. So y prime, the derivative of sine is cosine. And remember the chain rule, the derivative of kt is k. We need to multiply by k. Okay, and so now we have a y prime that we could plug in, but we do not actually have a y prime in this differential equation. We might at some point, and we would be able to replace it by this, but right here we have y double prime. So we need to take this derivative again. Y double prime, the derivative of cosine is negative sine, kt, and then once again we take the derivative of kt, and that's k times the k that's already there, so k squared. Okay, I might be running out of space here, so let's now plug that into this differential equation. Negative k squared sine kt plus 9y was sine kt equals 0. Okay, so I see we can factor a sine kt out. Sine kt times negative k squared plus 9 equals 0. Of course, we could set k equal to 0 or to pi. Actually, maybe we do want to set it equal to pi. No, sorry. So I was thinking, we just want to look here at negative k squared plus 9. If we set k equal to 0, it's not positive, so we actually can't. But if we set k equal to pi, for example, k equals pi, then anytime we multiplied t by pi, if t were an integer, then yes, this would equal 0. But t is not defined as an integer, so this will not constantly be 0. What I mean by that is, like, okay, sine of pi t. If t were 1, 2, 3, just the integers, yes, this would always be 0. But in this case, t is not defined to be in an integer, could be any real number. So this would not always be 0. At some points it will be 0, and that's fine, but it will not always be 0. We're looking to set this equation so that it will always be 0, even if it doesn't matter what t is. Okay, so sorry for getting sidetracked there. Oops, let's get rid of that. Okay. So we can set negative k squared plus 9 equal to 0, negative k squared plus 9 equals 0, negative k squared equals negative 9, k squared equals 9, k equals 3, and also negative 3, but it's asking for the positive values, so we'll say 3. Okay, so this is the derivative plug-in method. We took the derivative and plugged it in. Let's do the same for the next equation. Let's wall this off. Okay. Y equals cosine kt. Satisfying. This is the same differential equation. So I'm just going to go ahead and start taking the derivatives of y equals cosine kt. We're going to use the same method. Y prime equals negative sine kt. Once again, times k. And ddt again. Y double prime equals negative k squared cosine kt. If you have trouble remembering the trig derivatives, I always say if it starts with c, the derivative, you switch the signs, so derivative becomes negative. If it doesn't start with c, s or t, secant or tangent, we don't change the sign. So negative sign will not become positive cosine. Okay, yeah, let's plug in. So y double prime plus 9y equals 0. Negative k squared cosine kt plus 9 cosine kt equals 0. This is essentially the same thing as the last one. Cosine kt negative k squared plus 9 equals 0. And once again, we are just looking for the value that will always make this equal to 0. Doesn't need to depend on t. So we're setting k equal to 0 here, and we get k is equal to plus or minus 3 again, but this time we're looking for the negative value, so negative 3. Okay, onward. Match each differential equation to a function which is a solution. Okay, so we're going to use the same method here that we're using the last time, taking the derivative and then plugging it in. I think a good way for us to do this would be to take all of these derivatives and then to plug them in. And the reason is I don't think at this point you have the intuition of, oh, this function suits this differential equation well. Eventually you will, but not now. So A, y equals 3x plus x squared. We have y already, 3x plus x squared. Y prime would be 3 plus 2x. Y double prime would be 2. B, y equals e to the negative 2x. Remember the derivative of e to the something is e to the something times the derivative of the inside, negative 2. Y double prime be 4 e to the negative 2x. Where can I fit c? I think it'll come here. Y equals sine of x, y prime equals cosine of x, y double prime, negative sine x, d y equals x to the 1/2. Just remember is the square root function. Uh-oh. 1/2 x to the negative 1/2. Y double prime is negative 1/4 x to the negative 3/2. And I don't know if we're going to have space. Y equals, this exp is just e to the power of whatever. So e to the 7x, 14 e to the 7x, y double prime equals 14 times 7 is like 7 times 7 times 2, 98, 98 e to the 7x. Okay, so this is a lot, and there's a lot to plug in here. So let's try to do this as intelligently as possible. How do we do that? Well, if we look at 1, y double prime plus y equals 0. This is a good place to start. So the second derivative plus the function equals 0. So let's just kind of look through. The function plus the second derivative is 0. Not a, not b. C looks good. If we plugged in sine x for y, negative sine x for y double prime, this would equal 0. So we know it's C. So now we can stop looking at C. 2, the derivative is equal to 7 times the function. So 7 times the function, no. 7 times this, nope. Nope. But here, yes, y times 7 is 14. It's 14e to the 7x. So there we are. There's e. These are a little bit worse, the last two, but we've already gotten rid of a couple things, so that's good. Yes, so y double prime plus y double prime plus 9y prime plus 14y is equal to 0. Okay, so we can, once again, try this, try A, and I'm actually probably going to like write this work here. So y double prime is 2 plus 9, 3 plus 2x plus 14y, 3x plus x squared equals 0. Okay, so something to notice, we're not going to be able to cancel these x terms because we're adding. Everything is positive. We're adding everything. So there's no way this is going to equal 0. So it's definitely not A. But let's talk about that logic. We're y double prime plus 9 y prime plus 14y. So if everything is positive, there's no way it's going to equal 0. So we should just know that A is not our answer. Whereas B and D are better candidates because we do have positive and negatives. So let's go to B. Y double prime is 4 e to the negative 2x plus 9 times negative 2 e to the negative 2x plus 14 e to the negative 2x equals 0. Okay, so 4 e to the negative 2x plus negative 18, so that would be negative 14 e to the negative 2x plus 14. So that looks good. So that looks like it's going to be B. And that's good. We don't have to plug in. We don't have to mess with D. Okay, here we have, I was going to say this is the same where everything's positive in 4, but we would be subtracting by y, so maybe not. Maybe we should try this one with A. So 2x squared times 2 y double prime plus 3x, 3 plus 2x equals 3x plus x squared. 4x squared plus, what is that, 9x plus 6x squared equals 3x plus x squared. Okay, so I know I'm kind of running out of space here. If we add these, we have 4x squared plus 6x squared is 10x squared, and that's not equal to x squared. These sides need to be the same. I'm gonna erase C so we can have a little more space to see that. So this would be 10x squared plus 9x equals 3x plus x squared. These sides need to be exactly the same. And if we keep combining like terms, we have this, which is true for some values of x, but it's not true for all values of x. So we know that this number 4 is not a. So we know that it's d. And we know that it's d. We don't need to plug it in. But we would just do the same thing. We would just plug in and check. Okay. This should be the last problem. Find the value of k for which the constant function is the solution of the differential equation 2t cubed dx dt minus 2x plus 6 equals 0. Okay, so we have changed the variables here, which can be a little confusing, but it's really the same idea. Whatever the variable on top is sort of what we've traditionally thought of as y. So, this is normally dy dx, but now it's dx dt. So instead of like a y equals something x, we have an x equals something t. So when we take the derivative of x, we're taking it with respect to t. This should be familiar from calculus, but it's good to refresh. And you do see a lot of this in differential equations, so something to look out for. Okay, to find the value of k for which the constant function is the solution of this. Okay, so are we going to use the same method? Well, we have a function. And we have a differential equation, diff EQ, differential equation. So yeah, we're going to use the same method. We have x equals k, and we're going to take the derivative with respect to t. The derivative of x is dx dt, or we can write it as x prime, of course. But I'm using dx dt because that's what we see over here. The derivative of k, the derivative of any constant, is 0. And so now we can plug in. We have 2t cubed, dx dt is 0, minus 2x we know is k, plus 6 equals 0. So 2t cubed times 0 is 0, negative 2k plus 6 equals 0, negative 2k equals negative 6, k is equal to 3. Okay. Really, that's that on this problem. I think it might be worth noting that x of t written like this is the same thing as like y of t or y of x. Whenever we see x by itself, we can replace it with whatever x of t was. When you see something in a differential equation, it won't be written like this because it would get confusing. If we had minus 2x of t like this, it looks like we're multiplying x and t, whereas x parentheses t like this, x of t, says that x is a function defined by t. And so if we wrote it like this, it would get confusing because it would look like we're multiplying x and t. So we don't do that. Okay, this was, oh, well, we have another one actually. Let's do it. So for what values of r does the function y equals 10 e to the rx satisfy the differential equation? Y double prime plus 2y prime minus 24y equals 0. Okay, same deal, right? This is our function, and this is our differential equation. So it looks like we need two derivatives. We need the second and the first. So we take the derivative of 10 e to the rx. And it looks like we're dealing with x, so this is d dx, y prime, e to the rx times 10. 10 stays, e to the rx stays, and we bring down the r. Derivative of rx, derivative of this is y double prime, 10 stays, r stays, e to the rx stays. Derivative of rx is r squared, or is r, so we multiply by r squared. Okay, yeah, we plug in now, so 10 r squared e to the rx plus 2 r e to the rx minus 24 e, oh, I'm forgetting the 10, right? 2 times 10 r e to the rx minus 24 10 e to the rx equals 0. So it looks like we have a common factor in 10 e to the rx. So we can factor that out. 10 e to the rx, r squared plus 2r minus 24 equals 0. And some of you are seeing this and probably thinking about what we need to do. And it is funny that we're in like a very high level of math, and really to solve this, we really just need to be able to factor a quadratic to get our r values. And later we're going to learn that we kind of just know to do that, and we don't really have to mess with what we just did. But for now, this is fine. Once again, there's no r value that's going to make this permanently 0 in the e term, because e to any exponent is never 0. E to infinity is infinity. E to the 0 is 1. E to the negative infinity approaches 0, but it will never be 0. So we're not going to get r values from here. We'll just get them from here. So just think about this. Factoring this, we all have our own methods of doing this. R and R, positive and negative, plus and minus. Difference of 2, 6 and 4 to get 24. So minus 4 plus 6 to make this positive. So R equals 4 and negative 6. So the smaller one is negative 6, the larger one is 4. Okay, I think that, oh my gosh. All right, this is the last one. This is the last one. Okay. Find the value of k such that this is a solution of the differential equation dx dt equals kx. So, same thing. Derivative of our x d dt, because this is an x equation. X of t, my gosh, equals 5 to the t. The derivative of x of t is x prime, or let's say dx dt, just to keep things the same, dx dt. Derivative of 5 to the t. So this is similar to e to the x. I'm just going to, for anyone that has forgotten these derivatives, the derivative of e to the x is e to the x. The derivative of something, a to the x, is a to the x ln a. So this would be 5 to the t ln 5. Okay, and that's all we need here to solve. So dx dt is 5 to the t ln 5, and kx, x was 5 to the t, so k times 5 to the t. Get rid of our 5 to the t's, we have ln 5 equals k. So ln 5 is our answer. All right, that was a first homework assignment in a differential equations course. I hope this helped if you were doing similar problems or just didn't know where to start learning this yourself. And keep following along. We'll keep going.